Hi, everybody. Yes, thanks for the introduction, Brian. As Brian said, I'm David Lutterkort. This is how you can find me on the internet, on Twitter, and my email address. I put my email address there mostly because, as I understand, Bill Gates hands out money for people for forwarding emails. So if you see that, please include me. So I'm going to talk about containers and configuration and sort of the challenges that you encounter when you start doing things with containers more seriously and at scale. I'll talk about roughly the following things. First, I want to level set a little bit on what configuration is. It's one of those words where if you ask 5 people, you get 7 different answers about what configuration is. If you throw configuration management into the mix, you get even more variation. I just want to make sure we're all on the same page there. Then I'm going to talk a little bit about containers and immutability and some of the challenges there and some tips on how you can work around them. Build versus runtime with containers. Everybody knows you need to build images. We'll talk about that, and then we move on to some higher level things, the schedulers like Kubernetes or Mesos or Docker Swarm that are really, really useful when you're running containers. The examples I'm talking about are mostly drawn from Docker and Kubernetes and a little bit of Docker Swarm. That doesn't mean that the ideas here only apply to those. I hope it's general enough to make it clear that if you have a different container runtime or are interested in a different scheduler, that those ideas roughly apply there too. All right, so what is configuration? The current crop of configuration management tool has gotten us used to think of configuration management mostly as package file service, right? I'd argue that that's only one instance of a more general problem, and that solutions to the more general problem actually apply, for example, in the context of containers. It just so happens that package file service is really well suited to the world of long-lived servers, where you set up something once and then you keep changing and changing it to modify it to whatever it needs to be modified to. But for containers, the criticism is rightly that this is definitely not enough, and in some cases, package file service is also a poor fit. But the ideas behind that lead us to talk about package file service in the config management world totally apply. And to me, configuration, if you want to take it really broadly, is that configuration is any input into infrastructure. With that view, you can think of the systems you're running, or at least the software part of the systems you're running, as the actual code you're running, the applications, the data that those applications operate on, and the configuration that you apply to the running code. And the configuration is the difference. If you work on a travel website, the configuration is the difference between you booking tickets to Hawaii 100 times a day because you're doing some development and testing something out, and somebody who actually wants to buy a ticket on the live side getting charged for the ticket. Right? Nobody wants to be charged for the tickets that they're booking in development. And what makes the management of configuration tricky is that you need to both do this over time and at scale. Over time, it's really easy to set up a system once and walk away from it, or build a container once and just keep that running. But as time goes on, you have to make changes. You also need ways to track what those changes are and correlate the input to whatever your container builds back to the actual containers that you're running. And similarly, at scale, anybody can manage 3 machines. You log in every once in a while, make some change, maybe take some backup snapshot, and that's it. If you're working with 30 systems, that's probably all you're doing every day. Once you hit like 300 or more systems, you're definitely lying there crying for tooling and help with all the manual stuff you're doing. And so some of the core features of configuration management are that it makes it possible to describe different aspects of your systems in isolation. So you can talk about, this is how I set up a web server, this is how I set up a database, this is how I deal with NTP, what have you. And then be able to weave those different aspects into a concrete system, into a concrete image for a container or a concrete setup of a long-lived server. And those two things, I think, those ideas got really crystallized about 10, 12 years ago, and I think that's one of the things that led to a blossoming of config management tools back when Alva Kaut's paper about that came out first. Other benefits you get from configuration management is you get a common format for querying things, so you can ask questions like, who's all talking to this database? Where do I have OpenSSL installed? We saw some of that this morning in the keynote, which is really important for what we call situational awareness. And then specifically for containers, it's very unlikely that you're going to run all your infrastructure in containers. For starters, those containers have to run on something too, and that's not going to be containers. So yeah, config management also serves as a bridge across all the different technologies you use in your infrastructure and help you enforce common standards. Right, so a really simple example of how config management crops up with just running a single container is this here. Presumably, we're running a web app that wants to talk to a database. And the best practice in the Docker world for injecting what database to talk to is by setting environment variables. But that's already configuration data, right? The database you talk to is probably going to be different in development and in production, so that at least has to change between different environments. You might have to do maintenance on the database, and for that it's really, really helpful to know who's all talking to the database. So if you have a way to query which systems are talking to the database, these are all concerns that you need to address with config management. Similarly, this user bin check, this health command, sorry. Docker gives you a way to specify a health command, which it will run periodically to check that your container is still healthy and doing what it's supposed to do. But if I just give you an image of this web app container, how you're even going to know whether there's a health check in the container and where it is and what the command is to run it. This is another piece of configuration information you need to know to successfully run a container. Okay, so let's move to immutability and look at some of the challenges there. Here's a super simple application. It's running a basic vanilla Fedora container that doesn't have anything crazy in it. And the application is really just catting the system release file every second. It's very, very useful. So when we do that, I hope you're all admiring my awesome slide animation skills. This is what happens. And now I'm going to show you how you upgrade that container live at runtime. There's a command docker exec, and that runs a command in the context of an existing container. So while we're catting system release, we're also running set against system release and replacing 24 with 25. So when we do that, we're happily printing 24. We run docker exec, and then we're printing 25. And you can already see the update didn't quite work because we only replaced the number, but not the words that spell out 24. But that's kind of to be expected from such an ad hoc approach. All right, Docker also has a useful tool called diff that lets you compare what's in a running container with what's in the image. And sure enough, diff tells us that system release was changed because of our set command. All right, so the big lesson here is that containers are not immutable by default, even though everybody talks about containers as immutable infrastructure. When you first run them, they're not immutable. And they're sort of immutable the same way that packages are immutable, right? By convention, when you install something with a package, you don't modify anything that came with the package except for clearly marked configuration files. But I'm sure everybody here has, in a pinch, logged into a machine, changed some script in user bin to address some shortcoming, some bug, and totally violated that constraint. In the Docker world, you have a nice way to mark your containers as read-only. There's the read-only flag. And when Docker starts your container, it marks the file systems in the container as read-only. And so you can't make any changes. When we now try to do our awesome upgrade, we get an error message. And Docker diff actually tells us that nothing has changed, except for /run, but that's scratch data anyway. All right, so you should totally use the read-only flag with all your containers to avoid sort of the gap between the assumption you have that what's inside your containers is exactly what you built versus it's not necessarily the case, because those sort of things are the things that lead to hard-to-debug production outages. It's, when you debug a production problem, you're like, oh, this must be true, and this must be true, and because containers are immutable, this must also be true. And if that assumption is violated, you'll never think of the thing that actually causes the outage. I said here on the slide, enable read-only whenever possible. And that's a bit of a weasel word. That's sort of how my kids do homework. They do homework whenever possible, which means if there's no more Minecraft to play, no more friends to visit, all that. And to illustrate that a little, here's a really simple application. It's a very basic file upload application written in Ruby using the Sinatra framework. You could do the same thing with Python and Flask or whatever your framework of choice is. And it really only does two things. It has an upload, a get upload, where you get a form that lets you select a file and then hit the submit button. And then the post upload is the thing that this file gets sent to and that processes it. And what we do there is we take the file, write it to somewhere in our local file system. And that's the extent of the application. And so what happens when we run that with a read-only flag? At first, nothing, right? The container will start successfully. If we had a health check there, the health check would tell us everything's A-OK, up until the moment when somebody tries to use that. And what happens is that we stumble over this line where we want to write stuff into the local file system, which is now read-only. So that's not great. But arguably, because the point of the application is not to store files in the container's local file system, which then vanish when the container goes away, we should really use somewhere else to store that. And we pass in a volume. Right now we're saying the directory srv lolcat uploads should appear inside the container as app upload. Stuff gets written there. And both the data is now persistent, and we don't get the error with trying to write to a read-only file system. But again, that's configuration data, right? If you run multiple of those containers, you now need to make sure they all write to the same directory. If that directory changes for whatever reason, maybe your lolcat application becomes so popular that you need to move the storage from a host to a SAN or whatever, you need to know where all these places are that you need to make a change. And now we're good, right? Now we run this application, containers in read-only mode. We have a place to write files to, and everything's hunky-dory. Not quite. There's also this little subtlety about how web frameworks deal with uploads. When you send a file in your web framework to the server, the first thing your framework, Sinatra, but any other framework I know of does the same thing. What they do is they take the file, put it in a temporary directory, and then your application gets a pointer to that. But we are read-only, right? So this will fail because we're, again, trying to write to a read-only directory. And the way out of that is that Docker also gives us a tempfs flag that marks some directory in the container as temporary and writable. And now with that, we're really good. But again, we have a whole bunch of information we need to know to run this really stupid, simple application that you don't automatically can deduce from just looking at the container. You need to, there's a whole bunch of context you need to know about the runtime environment the container expects to run it successfully. Okay, so use tempfs to kind of punch holes into the read-only file systems of your container, to punch writable holes into that. Okay, and so the really big point about this, rather than just flags for Docker, is that the immutability of containers is really just a social construct. It's a convention, and like all such conventions, it might get violated. So what you really want to do is make sure you understand where you're making assumptions that aren't really provably true because of the technology you're using, and putting technical controls in place to make sure those things can't get violated, like the read-only flag. And the other question was, given a container, how do you know what the runtime environment expectations of that application are, and how do you describe that? One option, of course, is to go back to how configuration management was done for a long time by writing it down in a Word document, but that doesn't scale. All right, and so we're going to look a little more about how to put this information into containers in this section here, where I'm talking about build versus runtime. That's another place where containers sharply differ from sort of long-lived servers. On the one hand, the Docker tooling makes it really, really easy and is really, really nice around building container images. It's really pretty awesome. On the other hand, it's pretty much mandatory to split any sort of setup you do between image build time and runtime. So you need to be a lot more conscious about what goes where, and you want to do most of as much as you can at build time and as little as you have to at runtime. And so if I give you an image, there's all kinds of questions you might want to ask, like what machine and what environment was that image built in? How do you run this image? We just saw that. Who supports this image? If I'm running this in production, stuff blows up, who do I talk to? Was the image built reasonably and doesn't contain malware? Has it gone through some sort of scanning? These are all questions you might want to ask about images. And similarly, once you run stuff off those images, when you look at when you walk up to a container that's running somewhere, you might want to know, who built it, how was it built, what's the software in it? The container's called Apache. Does that mean it's really running the Apache web server, or did somebody decide to put another Apache project? God knows there's enough into a container. But even if it's running the Apache web server, does it have mod SSL in there? Does it have mod CGI in there? Is mod CGI configured in a way that lets it run things you can upload through the application, which is a great recipe for a miserable day. Is the software up to date? Was it up to date when the image was built? How much has stuff changed since the image was built? These are all questions you'll probably need to answer sooner or later if you're doing things seriously with containers. And the way you build images in Docker is by writing this something called a Docker file, which looks like this for that upload application I had earlier. What it says is, let's see if this works. Ooh. What it says is that we base this image on a vanilla Fedora image. Then we update everything in there, install Ruby and Bundler. Bundler is a package manager for Ruby libraries, for Ruby gems. Then we copy our applications into the container and run bundle to pull in the Ruby dependencies that our application has. And the stuff down here is about how you actually run the application. But if you look at that, there's all kinds of questions you might ask, right? Where did the base image come from? Did I build that this morning myself on my laptop? Does it come from like a blessed registry from Docker Hub or somewhere? Similarly, when you do all this package stuff, where do these packages come from? What repositories were used? What versions get installed? What versions of those packages get installed? Later, when you run this, does this have a vulnerable OpenSSL version in it? And similarly, when you copy the application in there, what was actually what's actually getting copied here, right? At what state was my application when I built that image? Is that bug that got fixed on Tuesday, is it actually in there now or not? And so, with most things, you should see how I get up in the mornings. Time is your enemy, and if you build this once, that's not a big deal. But you're going to do this over and over. How can you deal with the progression of time and the progression of the world around you? And more concretely, what are the right triggers to rebuild your images? Most people will have set up some sort of CI pipeline where a change to the application code will trigger a CI run, and at the end of it, some container image will fall out of it. But is that enough? And because I'm asking that way, it's not really enough. Right? You also need to rebuild based on external factors. Right? The packages you pull in, the Ruby gems you pull in will also change. And since it's incredibly hard to keep track of all those external dependencies, you're going to wind up with a system where you just periodically rebuild all your containers, say once a day or something like that. And that's probably limited by how many containers you have to rebuild, how much infrastructure you have to do those builds, and how fast you can move everything through there. The other thing is, all these questions I asked, really call for putting some metadata onto your containers. And Docker has this notion of labels, which are a really great way to actually put metadata during the build onto your images, so that when you run them, you have a way to answer some of these questions. And that, again, the package management is a great parallel there. This is the RPM metadata for the C library in Fedora, and you can ask questions like, what does this depend on? Who depends on me? Those are all great questions you want to ask, and you probably want to answer by embedding some metadata into your images. Some of the metadata actually gets put in there by default, just as a side effect of building images. For example, because we say this image wants a volume mounted at this directory in our Docker file, you can query that out of there. And that's great, but there's a lot of questions that doesn't answer, right? What sort of data actually goes into app uploads, right? What's the application doing there? Is it scratch data? Is it data that's really valuable and needs to be backed up? How much storage should you set aside for these things? There's no answer that you get from just this little snippet of metadata. Similarly, you can query out what the port is, or ports, there could be multiple, that this container wants to listen on, but you have no context about the port. What protocol is being used, right? What needs to be fed in there? You have no idea just from this. And so Docker labels, the way you use them is incredibly simple. You just put a snippet like this into your Docker file, and you can knock yourself out with the sort of information you're going to capture there. Maybe you want to remember what the release status is, mark things that aren't blessed for production as beta, alpha, whatever, so that if you find containers like that running in production, you can set off alarm bells. Embed the version of the software you have in there, maybe the Git hash of your app, from where your application came from, if you're using Git for version control. Maybe you also want to embed a pointer to the Git repository to make it easier to find things. And you can pull that out, that metadata, either from the image, like I do here. This is the name of an image, but you can also point it at a running container to get that same information out of it, which is really, really handy. And so another thing you should do is think about the metadata you need to capture to help troubleshooting issues later on. Unfortunately, there's no set standard yet for Docker labels and for how to express things. So you get to be creative and make up your own. But don't be shy with it. I don't think there's any practical limit on the number of labels you can embed in a container. But you don't have to just restrict yourself to this fairly static data. You can do other things. One really cool idea is to just stick the whole Docker file that you used to build this container into the container itself and have a label point to that, because then you can query out the label and the location of the Docker file, run Docker, and run, use Docker run to either cat it out of the image or use Docker exec to cat it out of a running container. And that takes away some of the mystery of how was this thing even built. So embed your Docker file in the image. So another really, really cool idea is that you might want to describe certain things in your images, right? And so you can set these labels to commands that can be run against your container. For example, if you want to list packages, you put a label like cmd.packages that tells you what command you need to run inside the container to list the packages you have in there. And now you can list packages independent of what the base OS of your container is, right? It's going to be a different command for Debian or Red Hat or Alpine, as in this case here. apk info is the Alpine command that lists packages. But now you have a basis for writing some tooling that can go through and actually figure out what are the OpenSSL versions in all my containers. And following, this is just an example of what happens when you query out what's the command, and then you just stick that command into a Docker run command, and you get a dump of the packages that are in the image. And so by doing that, you make your images discoverable, right? You can embed lots of other commands that help you find out other things about your containers. And in a way, you're building a very simple management API for your containers if you do that. All right, so we saw this morning about image building in the keynote. I assume pretty much everybody was at the keynote this morning. The demo of that was really, really awesome. Actually, yeah, the slide still shows this repo as private, but it's actually public now and on the Forge. And I highly recommend looking through it, because the way the image build works is you don't write a Docker file. You can use the existing Puppet content to actually build Docker images. So that's a really nice way to make sure that if you have certain policies around how Nginx should be run, that gets respected regardless of whether you're running bare metal servers or cloud or containers, because you can reuse the Puppet code that expresses your policies that way. And the way you use it is, it looks pretty much, what you write in Puppet looks pretty much the same as what you would write for a long-lived server, a traditional server. Here we're saying pull in Nginx, set up a vhost with this root for the static content it should serve. Then we copy some static content in there. And the one container-specific thing we need to do here is we need to tell Nginx to not demonize itself, because in the Docker world, the service needs to run in the foreground. It shouldn't demonize itself. But based on that, you can, and a little bit of metadata, mostly around the additional things that you need to know to actually run a container, like what command to run, what port to expose and allow connections from the outside to, and then the name of the image. That's all you need to write in addition to that to actually build the container then with Puppet Docker build. And the resulting container you can just run like any other container. There's nothing special Puppet specific about the containers that you build this way. But yeah, check it out. It's a great way to use your existing Puppet content in both use your existing Puppet content with containers. But also, if you're not using Puppet yet or not very much, it's also a great way to take advantage of all the features that Puppet gives you for how you describe things and how you structure your configuration and apply it in the Docker world. All right, so let's move on to sort of higher level concepts. Containers are really just the building blocks for more exciting pieces of infrastructure. Where stuff gets really, really interesting is with all these schedulers like Kubernetes, Docker Swarm, Mesos. There's a whole bunch of them. But since these are things you're also going to run, somebody also needs to think about how these things get configured. And so what these schedulers all give you is they give you additional abstractions on top of what containers give you. The most important one of them is that they let you treat a whole cluster of machines kind of as one machine. Instead of saying, run this container over there on that machine, you say, run this container somewhere in that cluster. And the scheduler will take care of placing that container onto a host that's both suitable and has space available. They also deal with simple changes in the number of resources you have. For example, if you add more hosts to your cluster, they can rebalance the workload across using the new resources. And they give you some fault tolerance. For example, in Kubernetes, you can say, make sure that I always have 4 copies of this web application running. And so if one of the hosts on which one of those containers runs fails, Kubernetes will detect that and spin up a new container on some other host so that you're back to running 4 copies of that same application. So those are all great. And the way you interact with them is that you express constraints. When you want to start a container, you say this container needs resources that look like this, so much CPU or so much storage or memory or what have you. The downside of this really nice constraint-based placement of containers is that the schedulers actually need to know a great deal about the resources they have available. And so you need to make sure that that resource information is accurate. Right? The way you do that, for example, with Docker Swarm is that when you start the Docker daemon on a host, you put labels on the daemon. So here we're putting labels on the daemon before we were putting labels into the images. It's the same idea, but slightly different thing. And here we're saying that this daemon has SSD storage. And then later on, when we place a container and we know that this application really needs SSD storage, we stick a constraint in there that says, put this container on a host that's marked that way. Kubernetes has similar ideas with the resources you can request, which is also constraint-based and based on information about the hosts you're running on. The big question, though, is that just because you start a Docker daemon and label it with SSD storage, that doesn't magically make an SSD drive appear in that machine. Right? It could well be that somebody copied some setup from somewhere else, didn't even know that this label is in there, and now we have a machine with a hard disk with spinning Rust that's labeled as SSD, and weird things will probably happen. So those properties and those constraints you feed into the scheduler, you want to compute them dynamically. And a really nice way to do that is to use the same tool that Puppet uses under the hood to figure out what nodes look like and use factor. For those of you who haven't seen it, factor, and I just had it print out YAML here, factor knows or can figure out a great deal of information about a system, like what disks are there. It sticks DMI information in there, how much memory you have, lots and lots of other stuff. And if the stock factor doesn't detect the things you need to detect, you can easily expand it by providing a shell script that figures out whether your drives are SSDs or hard drives or what have you. And so with that, your Docker daemon startup now looks something like that, where when you start the Docker daemon, factor goes and tries to figure out what the kernel version, for example, is. So but you're still dealing with like shell startup scripts. And if you now decide that you need additional things to constrain your placement by, right here we don't have storage. Now you decide that across your 100 Docker hosts, you need to add storage as an additional constraint. You need to make sure that all your daemons get labeled correctly. And that, again, becomes a little laborious if you have to do it manual, and very likely that you'll miss something somewhere. And so that's one place where the Docker platform module, which is a module supported by Puppet, where that comes in really handy, because it lets you say the class Docker sets up the Docker daemon, it installs packages, makes sure the Docker service is running and all that. And there you can just pass in what labels should be applied to the daemon. And so with a one-line change here, you make sure that a one-line change, then a run through the direct change tooling, the orchestrator, you make sure that all your machines are labeled consistently and uniformly. Okay, one other thing that schedulers introduce is that they don't just deal with running containers in lots of places or across lots of hosts. They also introduce some higher level concepts which are incredibly handy. For example, Docker has networks. I think all of them have the notion of networks, which are virtual network overlays over your physical networking to let you build custom networking. Kubernetes has a notion of services, which is really just a stable name for an actual service, so that no matter where something's running, you can connect to it in the same way. Kubernetes also has replication controllers, which is where you can say things like, I always want to have 4 of this sort of container running. Kronos is jobs. So there are lots of like higher level things that are built on top of the basic container foundation. The downside is that the way you interact with most of them is imperative. Like the APIs and commands you use to change things in them are imperative commands, and which is not really great for management. For management, you really want a declarative way to talk about the end state you want to get to, and ideally idempotent commands to do that. This here is actually how the Kubernetes documentation talks about how you change the image that's running in a Kubernetes service. I love that Set is involved there. I don't recommend Set as a tool for production, but it is what it is. Similar, like in Docker, when you create a network, first time, that's great. It works. Second time you try it, you just got an error. And if that's in a script, you're going to spend quite a bit of time figuring out what that error was. Was the Docker daemon not running? Did you make a syntax mistake in your network specification? Or is it really the fact that everything's okay and you're just getting an error because you're trying to do the same thing twice. And again, with a Docker platform module, you can make them very easy. You just write a Puppet resource down that describes what this network should look like, and Puppet will make sure that the network is present and running. Yeah, and that's the other bonus for how you deal with these things. Everything's in YAML. And I'm not talking about 5 lines of YAML. It's more like 500 lines of YAML that you deal with, and you're just getting lost in detail. Somebody asked me yesterday about CloudFormation, and I mean, there's a similar thing that you have hundreds and hundreds of lines of JSON, and the thing you're really interested in is like 1 or 2 small places. And yeah, the authors of the Borg paper actually recognized that, and I think what they're saying is spot on here, that JSON, any sort of structured data, JSON YAML, for all I care XML2, is a really good way to deal with in interfaces. Like that's what you want to feed to your systems, but it's not necessarily what you want to use to make modifications or to manage your systems. And so the real takeaway is that code plus data has lots of advantages over data alone, right? If you have code that generates your data, you can avoid lots of copy and paste problems. You can abstract away all the detail you don't care about, and think of a YAML file that you templated, and then you leave 3 or 4 places that get substituted in for the things you actually want to tweak there. Sorry. Yeah, and so in the case of Kubernetes, we have a Kubernetes module that Gareth wrote that lets you control Kubernetes, and actually behind the scenes, it does generate the gobs of YAML that you need to feed into Kubernetes, but you're not exposed to that. And because you're dealing with a programming language, if you need to make some decisions about what the namespace of this pod in the end should be, you can do that in a programming language that has if statements and variables and all that, which is much, much nicer to deal with than editing YAML files. The other nice thing is that you can use Puppet's facilities for composing stuff together, defined types, to codify certain patterns. Like one really common pattern in the Kubernetes world is that you take a service and a replication controller and put them together. And what that gives you is roughly a load balanced service that has a stable name. And that's really, really useful. And so you can very concisely express, this should be a load balanced service with a name that I can always find. You can actually use this controller service pair, and Kubernetes, the default example is this guestbook example, which is fed by lots and lots of YAML. You can actually set that up with this resource, with 3 instances of this resource. So from I don't know, 100 or more lines of YAML, you go down to like 10, 15 lines of Puppet code, which of course makes this all much more understandable. All right, so some parting words of wisdom. The big one from the first section is that make sure you understand where the gaps between what you assume and what's necessarily true in reality, that you understand these, because those are the gaps that really hard to debug production outages come riding into. If you want to use containers at scale and over time, you need to think about abstractions. You can't just deal with a bare tooling that's available. You need to build stuff on top of it. And finally, that as a discipline, configuration management is really, really concerned with giving you tools to build those abstractions and build those abstractions so you can minimize the risk that you run into in your production deployments. All right, if you want to learn more, there's a whole bunch of more talks on this and similar topics coming up. We have in the exhibition hall, there's a demo booth for Project Blueshift. Project Blueshift is sort of our umbrella term for all those infrastructure hipster type things. Then Deepak's going to talk later about specifically schedulers and Puppet at 4:45. Tomorrow morning, there's something I'm really, really looking forward to, is the keynote by Scott Colton. He's going to talk about this from an actual practical perspective, what he did to containerize his life. And then Gareth is talking tomorrow afternoon about actually running Puppet itself in containers, which is also super interesting as an example of taking a fairly complicated application and running it in containers and in its own right. All right, and with that, I have time for a few questions, I think, if there are any. No? All right, thanks all for coming.